All right. This Zoom session is being brought to you by the fractal picture of itself. I'll be doing that every day from now on. All right, here we go. Every class from now on. All right, for today, we'll be doing section 1.1. It all starts out. So, okay. Excuse me. There we go. All right, this is the very basics, distance and midpoint formula. We start with a Cartesian plane. Now, there's a concept of a number line, where a line is, for every point on the line would correspond to a number, an infinite decimal digit. Well, here's a two-dimensional plane, and for that, we associate every point on the plane with a pair of numbers. You draw two lines called axes at right angles through a point called the origin point. And for any other point P, you go over distance X and up a distance Y to make a rectangle. Therefore, and the coordinates of the point P is the ordered pair X by Y. All right, fine. So for every point, there's a pair X by Y, and for every ordered pair, there's a point P. And X by Y and Y by X are different numbers or different pairs, and they generally correspond to different points. All right. And given some points in the Cartesian plane, here and here, x1 by y1, x2 by y2, I ask, what is the coordinate of the midpoint M, and what is the distance between the 2 points? All right, midpoint formula is pretty easy. If you draw 2 points in the plane and we draw perpendiculars here, x1 here, point y1 here, distance x2 here, distance y2 here, then midpoint will have coordinates that are the average of the 2 points coordinates. So for example, here's x1 and x2, and midway between them is their average, x1 plus x2 over 2. Here's y1, here's y2, and midway between them is the value of y1 plus y2 over 2. So the midpoint has these coordinates, x1 plus x2 over 2 by y1 plus y2 over 2. So the midpoint is basically, you can think of it as the average point. So for example, midpoint between 3 by 4 and 5 by -4, it's 3 plus 5 over 2 by 4 plus -4 over 2. That's going to be, this is 8 halves or 4, this is 0 halves or 0. The midpoint is 4 by 0. Now, for the distance between the 2 points, we have to go back to a favorite theorem of mathematicians, something called the Pythagorean theorem, named after Pythagoras, a guy from ancient Greece. I can tell you all sorts of weird stories about him. He ran a mathematical cult, honest to God. He preached that number rules the universe, which means, he took for deep mystical significance and so on, never mind that. And there's some indication that he didn't actually discover this theorem, but he did give a proof of it and made use of it. Namely, if you have a triangle with a 90-degree angle at the corner between A and B, so it's called a right triangle, A, B, and C, then A squared plus B squared equals C squared. That's the Pythagorean theorem. And it goes the other way around. If A squared plus B squared equals C squared, then this triangle has a right angle here. Now, there are various proofs. Euclid gives a very rigorous proof. Here's a proof due to a mathematician from India. He drew 2 diagrams, this and this, and he wrote beneath it, behold, here's the idea. Here's a triangle A by B by C, and here's another like it, and another like it, and another like it. So we have 4 of these triangles. And you set them inside a big square with side A plus B, here, 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 and here. Now, we take the same square with side A plus B. We rearrange these triangles. We put this triangle down to the left, this triangle up to the left, down to the right, up to the left, this triangle down to the left, this triangle up to the right. So we get this. And now you have to prove that these are in fact right angles. That's a non-trivial thing. So we get this area. These are 4 triangles, so the same 4 triangles. These are the same big squares, so their areas are the same. So the remaining areas must be the same. This is a square with side A, so its area is A squared. This is a square with side B, so its area is B squared. Now this, because this is a right angle, this also is a square, and it is side C, so its area is C squared. So therefore, A squared plus B squared equals C squared. Behold. So for example, here's a classic 3, 4, 5 triangle. 3 squared plus 4 squared is 9, plus 16, that's 25, which equals 5 squared. So this is a right angle triangle. Now, after I finish this, I'll go to the extra credit sets, and we'll talk about general Pythagorean triples. We'll see more about that later. Now, from the Pythagorean formula, we'll derive something called the distance formula, namely, given point x1 by y1, this point x2 by y2, then, and d is the distance between them, then the formula is something like this. Okay, first, between this point x1 and this point with coordinate x coordinate x2, this distance is the difference x2 minus x1. This point is at height y2, this one is at point y1. So the distance here, this vertical distance, is y2 minus y1. So we have a right triangle with sides x2 minus x1, y2 minus y1, and d. And therefore, by the Pythagorean theorem, d squared equals y2, x2 minus x1 squared. I write it the other way around, it doesn't matter. Squaring negative is the same as squaring a positive. Square this, y1 minus y2 squared. So d squared equals x1 minus x2 squared plus y1 minus y2 squared. And therefore, taking square roots, d is the square root of the sum, the squares of the differences in the coordinates. That's 4 ofs in a row. Square root of sum of squares of differences, whatever, of coordinates. Now, for example, here's a point -2 by 15 and -7 by 3. What's the distance between them? Okay, -2 minus -7, square that. 15 minus 3, square that. -2 minus -7 is -2 plus 7 is 5, 5 squared. 15 minus 3 is 12, 12 squared. 5 squared is 25, 12 squared is 144. Their sum is 169. The square root of 169 is 13. So this relies on what's called a 5, 12, 13 triangle. So some examples. You'll notice I have these number problems, odd numbers. Those odd numbers are a little bit obsolete because it refers to a previous edition, but they're not assigned in any case. So we proceed. Now here we have 2 points, 3 by -4 and 5 by 4. What's the distance between them? Okay, square root of sum of squares of differences, 3 minus 5 here. -4 minus 4 here. 3 minus 5 is a -2, square that. -4 minus -4 is a -8, square that. This will be 4. This will be 64, square root of 64, which is square root of 68. Now, we can reduce this a little bit because 68 is divisible by 4. So you break this into root 4, root 17. The square root of 4 is 2, so you get twice the square root of 17 is the distance between those 2 points. Here we have 2 points, -3 by 2 and 6 by 0. What's the midpoint? Well, x coordinate is -3 plus 6 over 2. Y coordinate is 2 plus 0 over 2. This will be 3 halves. This will be 2 halves. Or in other words, it's 1.5 by 1 is the midpoint between these points. Here we have a little bit more tricky problem. What points on the x-axis are 6 units away from 4 by -3? Okay, we start off, if a point is on the x-axis, then it's of the form x by 0. If it's 6 units from 4 by -3, then x minus 4 squared plus 0 minus -3 squared equals 6 squared. That's the distance formula. All right, so this is x minus 4 squared plus 9 equals 6 squared. Transpose the 9, x minus 4 squared equals 36 minus 9. So x minus 4 squared equals 27. So x minus 4 equals plus and minus root 27. 27 can break into 9 times 3. So x minus 4 is plus and minus root 9 root 3. Root 9 is 3. So x minus 4 is plus or minus 3 root 3. And transposing a 4, x is 4 plus and minus 3 root 3. So the points on the x-axis are 4 plus and minus 3 root 3 by 0. These points are 6 units away from 4 by -3. This one's a little bit tricky. Here we're given a point and a midpoint. Find P2. So instead of finding 2 points and the midpoint between them, we're given a point and a midpoint to find the other point. So what is P2? All right, we'll give it the coordinates x by y. So the midpoint will be x minus 3 over 2 by y plus 6 over 2. And this point is -1 by 4. So x minus 3 over 2 is -1 here. Y plus 6 over 2 is 4 here. And so, okay, we have two equations and we solve them. X minus 3 over 2 is a -1, so transpose the 2. X minus 3 is -2. Here we multiply both sides by 2. Y plus 6 equals 8. Here we add 3 to both sides, so x equals 3 minus 2, which is 1. You subtract 6 from both sides, so y is 8 minus 6 is 2. X is 1 and y equals 2, so the second point is 1 by 2. And there's the answer. Here it's getting a little tricky. We have 3 points. And the question is does that form a right triangle? Does it form an isosceles triangle? A right triangle has a right angle at one of the corners, and so it has a squared plus b squared equals c squared. An isosceles triangle has two equal sides and a base. Now, okay, to find right triangle and isosceles triangle, we determine distances. The distance from P1 to P2, well, it's square root of -2 minus 0 squared is -2 squared plus -1 minus 7 squared is -8 squared. This works out to root 68, which simplifies to 2 root 17. Distance from P2 to B3, root of sum of squares, 0 minus 3 squared plus 7 minus 2 squared, that's a 5. -3 squared plus 5 squared is a 34, therefore root 34. Distance from P3 to P1, 3 minus -2 squared is a 5 squared. 2 minus -1 squared is a 3 squared. Root 5 squared plus 3 squared turns out to be root 34. Okay, so root 34, these are equal, so this is an isosceles triangle. And if you square these, root 34 squared plus root 34 squared does in fact equal root 68 squared. So this is also a right triangle. So this is an isosceles right triangle here. Now here we have a picture of a baseball diamond with 90 feet on a side. How far is it from home plate to second base? Well, okay, like this. Well, this is a right triangle here. The side's 90 feet by 90 feet by d. So d squared equals 90 feet squared plus 90 feet squared. That's twice 90 squared square feet. And so taking square roots, you get root 2 times 90 feet. So it's 90 root 2 feet, which is approximately 127.28 feet. And I'm only doing it to 2 decimal places because going further, you'd be measuring the distance in fractions of an inch, which is ridiculous, seeing the plates themselves are about a foot across. And so this is actually a little bit more places than necessary, but that's all right. Well, so there we have for that. Here we have a triangle with vertices -2 by 5, 1 by 3, and -1 by 0. Prove that it's a right triangle and what is its area. Now this is a proof problem. So I will ask you to go in the homework to go through the steps. So, okay, we find AB squared, BC squared, and CA squared. AB squared, that's -2 minus 1 squared plus 5 minus 3 squared. That works out to 9 plus 4 is 13. BC squared is 1 minus -1 is 2 squared. 3 minus 0 is 3 squared. So that's 2 squared plus 3 squared, that's 4 plus 9, again makes 13. And CA is squared is -1 minus -2 squared plus 0 minus 5 squared. That comes with the 1 plus 25 is 26. Well, 13 plus 13 equals 26. So a squared plus b squared equals b squared plus bc squared equals ca squared. So yes, it is a right triangle, and the right triangle is at this shared point, B. The area of that triangle is 1/2 of base times height, because it's half of this rectangle with area h times b. And okay, so it's 1/2 AB times BC. 1/2 of root 13 times root 13 is 13 over 2 is the answer. Okay, that's good for that. Now, before we go on, I'd like to make a little comment, a little excursion over to the extra credit sets. This specific extra credit problem, the Pythagorean triples. A Pythagorean triple is a triple of numbers a, b, and c, so that a squared plus b squared equals c squared. So a, b, and c are whole numbers whose sides are the sides of a right triangle. All right, now, first thing I ask you to prove this identity and show all steps that if you have m and n, any integer, any numbers at all, then the square of m squared minus n squared plus the square of 2mn equals the square of m squared plus n squared. So make a proof of this algebraic identity. That's a point. So therefore, this is a right triangle. One side is m squared minus n squared, another side is 2mn, and the third side is m squared plus n squared. So, and for any choice of m and n, this will be a Pythagorean triple. Triple whole numbers, which are the sides of a right triangle. So for example, if you make m be 2 and n be 1, then if you work it out, get a 3, 4, 5 triangle. If n is 3 and n is 2, and if you work it out, you get a 5, 12, 13 triangle. If m is 4 and n is 2, then you get a 12, 16, 20 triangle. Now the thing is, 3, 4, 5, and 12, 16, 20 are in proportion to each other. 4 times 3 is 12, 4 times 4 is 13, 4 times 5 is 20. So the 12, 16, 20 triangle is a 3, 4, 5 triangle 4 times bigger. Here's a 3, 4, 5 triangle, make it 4 times bigger, and here you get a 12, 16, 25 triangle. These are called similar triangles. Not only are their sides in proportion, but they have equal angles. So be it. Now, if you want, so this proving this algebraic identity is worth a point, and this is worth 4 points. Namely, find 4 Pythagorean triples that are not similar to the 3, 4, 5, the 5, 12, 13, or each other. So basically, you have to choose m and n and make sure that you don't get basically the same triangle in each case. There we are. So okay, let's proceed. Excuse me. Excuse me, this is acting weird. Okay, we have concluded our first section. Just a second, let's